Hello, my name is Rajashekar Kaliki. I'm a maths teacher. This tutorial is on probability for the ninth grade math students, CBSE math students. And this is about a 1 hour tutorial covering the entire probability chapter with examples and real problems solved. And it's possible that you may not be able to do the entire tutorial in one shot. So feel free to cover first section and pause and come back later and do the second section. But by the end of this entire tutorial, we would have covered the entire ninth grade CBSE math probability chapter. And after completing the tutorial, you would be able to pick up the ninth grade maths textbook and start solving problems on your own or any other ninth grade level probability problems. So let's first start discussing what is probability. Have you heard statements like this? It will probably rain today. I doubt if the train will be on time. There are high chances that the price of diesel will go up. India will most likely win the match today. In all of these statements, the words that are bold, they indicate a certain level of uncertainty. For example, if you pick the first sentence, it will probably rain today. What are we trying to say here exactly? We are saying that we don't exactly know if it is going to rain or not, but it is likely going to rain, most likely going to rain. So there is more chance of raining than not raining. That's what we're saying here, right? Probably. And similar thing can be mentioned about other statements also. Okay. So the words, all these words that are in bold here indicate a level of uncertainty. In mathematics, such uncertainty can be measured numerically using probability. Now let's understand probability scale. So we mentioned that the probability is a number. It's a numerical representation of uncertainty. So the moment it's a number, it has a scale, number scale. On the rightmost end of this number scale, you will notice probability of 1 or probability of 100%. And such events with probability or certainty of 100% are called certain events. Okay, certain events. On the other end of the same number line, you will notice these will be events with 0% chance, 0% probability of happening. Such events are called impossible events. Impossible because such events will not happen at all. One example of a certain event for sure. Let us pick up dice. Okay, if you roll a die, the die has numbers from 1 to 6 on each side of the die. On the 6 sides, numbers from 1 to 6 are written. So if you roll the die, what is the probability, what is the chance of a number less than 7 showing up? It's 100% chance. This is a certain event. Certain event because the number is definitely going to be less than 7. Let us say the question now is, if you roll a die, what is the probability of number 7 showing up? That is 0. It's an impossible event. Why? Because the die is numbered from 1 to 6. There is no 7 on that die. So this is an example of an impossible event. Okay. And between the certain events and impossible events, there are events with equal chance, 50% chance of happening. What would be a good example of this? flipping a coin. If you have a coin, if you flip it, if you toss it, you'll either get heads or tails. What is the probability of getting heads? That's 50%, 1 by 2. What is the probability of getting tails? That's 50% as well, 1 by 2. So this is an example of an equal chance event. An equal chance event is an event which has probability of 50% or 1 by 2. And any event which has less than 50% probability, such event is less likely to happen. Any event which has more than 50% probability, more than 1 by 2 probability, is more likely to happen. Okay, so what did we learn so far? Probability is a numerical indicator of how likely something will happen. Probability can be expressed either as a fraction, decimal, or percentage. You can notice on this number line that we have written in percentages. Okay, 0%, 50%, 100%. We've also expressed in fractions, 0, 1 by 2, and 1. Similarly, you can also express in decimal number. So probability can be expressed as a fraction or a decimal number or as a percentage. And the other thing we know about probability is it is between 0 and 1. Okay, these are the things we have learned so far about probability. Now, let's discuss the concept of theoretical probability. Later on in this tutorial, we will also learn about something called empirical probability or experimental probability. Before going there, let's first understand theoretical probability. Theoretical probability is about probability that is mathematically possible. Let's understand this formula here. Theoretical probability equals to, by the way, it is written as P and E in the brackets. This says probability of event E happening is number of favorable outcomes for that particular event divided by total number of outcomes. Now, we use these three standard examples in most of the probability discussions. Let's start with a coin. If you toss a coin, what are the possible outcomes? Okay, you can either get heads or tails. So total number of possible outcomes are 2. Okay. Now let's say someone asks you, what is the probability of getting a heads when you toss a coin? And what is a favorable outcome when we say getting a heads? That is this particular outcome, heads. So there is only one out of the two outcomes. One outcome is favorable. So the probability of getting a heads is 1 out of 2, 1 over 2. Okay, that's about a coin because it has two possible outcomes and one of them is favorable. Let's think about dice problems. Okay, you have a die, and die again is a cube shaped object with 6 sides numbered 1 through 6. Okay, so what are the, if you roll a die, what are the total number of possible outcomes? That is 6, right? Because it has 6 sides and 6 numbers. Let's say someone asks you, if I roll a die, what is the probability of getting number 3? So how many sides have number 3? Only one of the sides. So one outcome is favorable. Okay. So 1 over 6 is the probability of getting number 3 when you roll a die. Now let's look at this interesting spinner. In this spinner, how many colors are there? 4. Red, green, blue, and yellow. Let's say you spin this spinner and someone asks you what is the probability of landing on a green when you spin. Okay, this is also reasonably simple. How many total number of outcomes possible? 4, because we have 4 colors. of those one outcome, the green outcome is favorable. So the probability is 1 over 4. Okay, so this is about theoretical probability. And like I said, coin, die, spinning wheel, these are some standard examples used in theoretical probability. Now let's take some examples and solve them. We have looked at one single coin earlier. Now let's look at tossing two coins. Let's say we pick two coins and toss them together. What is the probability of getting? There are two problems listed here, A and B. First problem is exactly two heads. Let's think over this. So we are saying we are going to toss two coins together. So if you toss two coins, the first thing we need to ask ourselves is, what are the possible outcomes? Let's see here. So what can we get? We can get a head, heads, heads, because it's two coins. This is coin number one, this is coin number two. Or we can get heads, tails, or we can get tails and heads, tails on the first coin and heads on the second coin, or we can get tails on both coins. Did we cover all possible outcomes here? Yes. So there are four possible outcomes. In these four possible outcomes, the question is, find the probability of getting exactly two heads. Exactly two heads is only one outcome is favorable. So what is the probability? Probability equal to, we have total of four outcomes. Out of those, one outcome is favorable with exactly two heads. So probability is 1 over 4. Now let's look at second problem here. This says find the probability of getting at least one head. What does at least mean? You either have one heads, or two heads, because we are rolling or we are tossing two coins, we'll at most get two heads anyway. So either one or two. Let's see here. So which of these, let's erase this first one. Okay. So from these four outcomes, which outcomes are favorable to at least one head? This one, this has two heads, so this is favorable. One heads, favorable. One heads, favorable. This has no heads, not favorable. So how many outcomes are favorable? 3. So the probability of at least one head, P, equal to 3 outcomes favorable out of total of 4 outcomes. So we have solved two example problems about tossing two coins together. Now let's look at another set of examples, this time rolling three coins together. Okay, we are just increasing the complexity of this problem so that we'll get these concepts very clear. So if we now roll three coins together, find the probability of getting, there are three different problems here. So now before trying to solve the problems, let's again list the possible outcomes. Now we are talking three coins. Okay, so three coins. Let's again begin writing the possible outcomes. We can either get heads, 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 or we can get heads, heads, tails, or we can get heads, tails, heads, or we can get heads, tails, tails. Now similarly, first coin can also become tails, right? So tails, heads, heads is another possible outcome. Tails, heads, tails, 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 heads, and tails, tails, tails. Now, if you're getting a little confused about how did I arrive this, I have a small technique here. You may want to make a note of this. First started off writing heads, all heads. Then I said, let's say the third coin here, I'm just going to make it tails because I've already covered heads. So tails, keeping the other two same. Once the third coin is covered, then I went to the second coin. And here I said, earlier I did heads and heads for second coin. Now let me do tails. And again, same options. Third coin will become heads or tails. So that's how I listed. Then I covered these first four. Then the remaining four are taking the first coin to be tails. Anyway, I hope you get that concept. So total, how many outcomes do we have? 1, 2, 3, 4, 5, 6, 7, 8. Total of 8 outcomes. Okay, so our denominator is known for all of these. Now let's see. Problem A, exactly 2 heads. Okay, how many of these outcomes have exactly 2 heads? Exactly 2 does not cover this. The first one is 3 heads. So the second one has exactly 2. The third one has exactly 2. Fourth one, only 1 heads. Here again we have exactly 2. Then we have here only 1 heads, 1 heads. Okay. Looks like we have 3 favorable outcomes with exactly 2 heads. Let's say 3. 3 over 8. That is the probability of exactly 2 heads. Now let's look at least 2 heads. This time we'll circle. Okay. At least 2 heads means either 2 or 3 because we are tossing 3 coins. Okay, so this is covered. This is covered. This has 2, at least 2. So this is also covered. This doesn't have at least 2. This has 2 heads. So this is also within our favorable outcomes. And not this, not this, not this. So how many outcomes are favorable? 1, 2, 3, 4. So at least 2 heads is 4 over 8. Wonderful. Pardon my handwriting. I'm trying to use a tablet here. Now the last problem here. Find the probability of getting no tails. No tails at all. Well, there is only one such outcome. All heads. Okay. So this is very simple. Out of 8 possible outcomes, one outcome has all heads. In other words, no tails. 1 over 8. Good. So what did we do here? We solved 5 problems altogether with multiple coins, tossing multiple coins. Okay, let's now increase the complexity a little bit more. So playing cards. Playing cards is one of the most commonly used examples in probability. It's possible that you may not already know a playing cards deck. So I'm going to cover the basics to begin with. If you can get a deck of playing cards and see them for yourself, that will be very helpful if you don't already know. A playing card deck, a standard deck has 52 coins altogether. How many? 52 coins, no, 52 cards altogether. In the 52 cards, there are 4 suites. Diamond, hearts, spades, and clubs. And if you notice, diamonds and hearts are in red color, spade and clubs are in black color. And in each suite, we have 13 cards. Interestingly, the cards are numbered from 2 to 10, that is 9 cards. Then J for Jack, Q for Queen, and K for King, and A for Ace. Okay, sometimes people use A here in the place of 1, but sometimes they put it after the King. So altogether we have 13 cards in each suit, and we have 4 suits. Okay, so that is 52 cards. Now let's look at these problems, and whatever we need to know to solve these problems, we'll discuss them. A card is drawn from a well shuffled well shuffled. Pack of 52 cards. Find the probability of a red color card. Let's start with this simple problem. We said there are a total of 4 suites. Of those, 2, the diamonds and hearts, are red color, and each suite has 13 cards. So this has 13, this has 13. Oops, look at the handwriting there. This has 13, this has 13. And I'll feel uncomfortable with this, so let me erase and write this 13. So how many red color cards altogether? 13 plus 13, 26. So out of the total cards of 52, we have 26 red color cards, which is 1 by 2. Perfect. So that is the first problem. Done. Let's look at the second one. A hearts card. What did we say? This is hearts. There are how many hearts cards in this entire deck? 13. So the probability of hearts card is 13 by, why did this 3 not show? 13 by 52, which is 1 over 4. 2 of spades. Let's see, what did we say? In each suite, we have 13 cards and 2 is one such card. But the spades 2, there is only one card. Okay, anyway, since we don't have space here, I'll write on this side perhaps. So there is only one favorable outcome out of the 52. So the probability of drawing 2 of spades is 1 by 52. A card numbered 6. Notice here, it doesn't matter which suit, it doesn't matter which color, as long as the card has number 6. So there is number 6 in diamonds, there is number 6 in hearts, there is number 6 in spades, there is number 6 in clubs. So how many cards with number 6? There are a total of 4 cards. So 4 out of 52. And this is 1 over 13. Perfect. A numbered card. What is the probability of finding a numbered card? Well, this would be interesting. Let's see, how many cards did we say? What is a numbered card? Any card with a number on it. And which cards do not have a number? These 4 cards, Jack, Queen, King, and A. They do not have a number. All these other cards, 2 to 9, 2 to 10, have numbers. So how many such cards? There are 9 cards. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 cards in each suite. The total of 4. So 36. So this is 36 over 52. I'll not simplify this for you. Or maybe I will 9 over 30. Okay. So this particular section of problems on playing cards is a very important section. A lot of times you will see in tests and exams probability questions using playing cards. If you don't know the playing cards set or deck, it's worthwhile just opening one and see. All right, let's move on. All right, on this slide, we have 3 problems. And I would like you to, once you see each problem, I would like you to pause the video, try to solve that problem, find an answer on your own, and come back and verify the answer. Continue the video and verify the answers. First problem. If you pick an integer, between 1 and 100, what is the probability that it is a multiple of 5? And similarly, what is the probability that it is not a multiple of 5? Okay, this is the first problem. So please pause the video, try to solve it on your own. Okay. Now, so multiple of 5. So what are the integers between 1 and 100? Let's assume that that includes 1 and 100 also. What are the integers between 1 and 100 which are multiples of 5? So I've written them down here. That would be 5, 10, 15, 20, etc., etc., all the way up to 100. And how many of these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So of course there are 20 numbers which are multiples of 5 between 1 and 100. So what is the probability now? Of the total number of numbers, which is 100, 20 or 20 are multiples of 5, which is 1 over 5. The probability of finding a number that is multiple of 5 is 1 over 5. Now, what is the probability that it is not a multiple of 5? Now that's easy, right? So we know that 20 numbers between 1 and 100 are multiples of 5. So how many numbers are not multiples of 5? That would be 80. So 80 over 100, which is 4 by 5. The probability that the number is not a multiple of 5 is 4 by 5. So I hope you got these both problems. Now let's look at the next one. Number 2. Here also we have A and B. Find the probability of the following. Getting a number less than 8 when a single die is rolled. Less than 8. Less than 8. Okay, single die is rolled. It's only one die. And one die has numbers from 1 to 6. So when you roll it, you will get either 1, 2, 3, 4, 5 or 6. So you'll get 1 to 6. So getting a number less than 8, all those numbers are less than 8. All those numbers are less than 8. So getting a number less than 8, the probability is actually 100% chance. That is 1, probability of 1. So such events are also called certain events. Okay, so we got this. Let's look at the next one. Getting an equal number of heads when 5 coins are tossed. Okay, so here we are tossing 5 coins. Now you can't get an equal number of heads and tails because 5 is an odd number. 5 is an odd number. So you will either get 1 heads, 4 tails, or you will get 4 heads, 1 tail, or 2 heads, 3 tails, or 3 heads, 2 tails, or all 0 heads and 5 tails, etc. Right? So it's just not possible to get equal number. It's not possible to get an equal number. So such an event is called an impossible event. An impossible event with probability of 0. Okay, so that's the probability of 0. Let's look at the next problem. Okay, these are simple true-false questions. If you flip a coin, there is an equal probability of seeing heads and tails. Well, this sounds like very straightforward. True. If you flip a coin, you either get heads or you'll get tails, and there is 50-50 chance. So equal probability of seeing heads and tails. That's done. Now, next question. So here, probability can be expressed as a fraction. Of course, it can be expressed as a fraction. Between 0 and 100. Okay, this sounds interesting. So between 0 and 100, the fraction, probability fraction is between 0 and 1. It's not between 0 and 100. Okay, so probability is between 0 and 1. And so this is false. This is false. I hope you also got these answers right. Now I'm going to introduce you to empirical probability or experimental probability. So in experimental probability or empirical probability, let's start off with by understanding what is the difference. When I was describing theoretical probability, I said that it is what is mathematically possible. So mathematically, theoretically possible. If you flip a coin, theoretically you can get either heads or tails. When it comes to experimental probability, it is always about an already performed experiment or an already available data. You have already tossed the coin 100 times, and from those observations, you want to calculate probability. Or you have collected some data from a classroom, from some people, right? And from that, you want to calculate probability. In such cases, we will use empirical probability. And the formula is very similar. Total number of trials in which the event E has happened over total number of trials. Number of trials in which the event E happened over total number of trials. Let's see this with an example, a simple example. Okay. In this example, in a cricket match, a batswoman hit a boundary 6 times out of 30 balls. Okay, she was served 30 balls. She played 30 balls, and out of that, 6 times she hit a boundary. Find the probability that she would hit a boundary on the next ball she plays. Okay, so this is not theoretical. What do we know here? What data do we have here? She played 30 balls. Of those 6 times, she hit a boundary. What is the empirical probability here? Total number of trials, total number of balls she played is 30. Of those, 6 times she hit a boundary. 6 over 30 or 1 over 5 is the empirical probability that she would hit a boundary next ball she plays. So probability of batswoman hitting a boundary is total number of times she hit a boundary divided by number of balls she played, which is 6 over 30, which is 1 over 5. Okay, I hope you understood this concept. We can do some more problems so that we completely understand. But before that, let me introduce you to some terminology. Okay, terminology of probability. Experiment. So an experiment is a planned operation carried out under certain controlled conditions. Okay, the words sound very interesting, but let's take a simple example. We decided to roll a die 30 times. That's our experiment. We'll just roll it 30 times, one after the other, and record the observations. That's our experiment. Okay, that's a simple experiment. We'll cover more and more examples later. Now, in an experiment, each iteration of an experiment is called a trial. Okay, in our die experiment, we said we'll roll the die 30 times. Each roll of the die, each one of those is a trial. So how many trials do we have in this experiment? We have 30 trials in this experiment. So experiment, trial, and then the concept of outcome. We've already used this word outcome multiple times in this tutorial so far. In each trial, what are the possible outcomes? So in our die example, each roll of a die can result in 1, 2, 3, 4, 5 or 6. So these are 6 possible outcomes of each trial. So that is this word outcome. Now this most important word here, event. You have already observed that we used prop P of E multiple times. Okay. E here is the event, probability of an event. An event is something that we'll calculate probability about. And it is, we can define our own. We can't define outcomes on our own, by the way. That is because when you roll a die, you would exactly have 6 outcomes. These are the faces of the die. But events we can define depending on the problem we are trying to solve. I've given examples of 3 events here. Event number 1, rolling an even number. In our die example, we can say what is the probability of rolling an even number. So that is, in that particular example, event is rolling an even number. Of course, 3 outcomes are possible which will compose this event. Okay, whether it's number 2, number 4, or number 6, that will come to later. But this is one event. Another possible event, rolling a number less than 4, that's an event. Rolling a 6, that's an event. So these events can be defined. Any number of such events can be defined about this experiment. These events are typically those for which we are interested in calculating probability. Okay, so for we basically calculate the probability of an event. So these are the 4 terms related to empirical probability: an experiment, a trial, outcome, and event. You will notice that these terms are used in the probability examples, so it's important to know the basic meaning of them. All right, let's use the same die experiment to do actual problem solving. This is an experiment with a die. And what did we do? We rolled the die 30 times. Number 1, first time is written here, all the way up to 30 times here. Each time we rolled, we noticed the outcome. Notice these terms here. This is outcome. This is trial. In each trial, we noted down the outcome. First trial we got 5. Second trial we got 4. Third trial we got 3, etc., etc. We noted all of these down. Then we want to do some problem solving using this data. So how do we do? This is a very large table. It's hard to understand. Let's first do a frequency distribution table. I hope you already covered this in your statistics chapter, or otherwise also it's fairly easy to understand. In this table, what are we going to do? We are going to write down all possible outcomes, and under each outcome, what is the frequency? How many number of trials actually have that outcome? So let's see 1 here. How many times do we have 1? 1, 2, 3, 4. Okay, I hope I didn't miss anything. 4 times we got outcome of 1. Let me erase these circles here. Okay, then 2. Let's see here. This is 1, 2, 3, 4, 5. Okay, 5. What about outcome 3? 1, 2, 3, 4, 5, 6. So 3 has shown up 6 times. What about 4? 1, 2, 3, 4, 5, 6 times. 5, 1, 2, 3, 4, 5, 6. This is 6 times as well. Interesting. Number 6. How many times did 6 show up? 1, 2, 3, and looks like that's it. Okay, did we get all these numbers? Let's see this here. 6 plus 6 plus 6, 18, 22, plus 5 plus 3. Okay, all 30 are captured here. Now let's compute probabilities of different events. First one here, probability of rolling a 6. Okay, let's see. Total number of times you roll the die is 30 times. Out of these 30 times, how many times did 6 show up is 3. So 3 over 30 or 1 over probability of an even number. Okay, so which are even numbers? 6. We have circled this. 4 and 2. These are even numbers. I should have circled these on the top. 2, 4 and 6 anyway. So that's 5 plus 6, 11 plus 3, 14. 14 over 30. That is the empirical probability of getting an even number from this experiment. What about less than 4? Less than 4 would be which 3 outcomes? These 3 outcomes. Now I'm going to put a big circle around these 3. This is less than 4. 4, 5 and 6 are excluded. Now this is how many? 4 plus 5, 9 plus 6, 15. So 15 over 30. Okay, I'm not going to simplify them. So I hope you get an idea. We have done one experiment with a die and we rolled it 30 times. We made a note of outcomes in each of those 30 times. We prepared a frequency distribution table from this and we calculated probabilities of 3 different events based on this experiment. Now, most of the times in tests and exams, you'll probably not get this table. You'll only get this frequency distribution table. Somebody will say, we've rolled the die 30 times and the number of times 1 showed up is 4, the number of times 2 showed up is 5. All of this data they will provide in a table to you, this table. Then they will give probability problems around this. So the first table I've shown in this particular tutorial purely to simplify to help your understanding. But typically this table is given as data and you solve problems on that. Okay. Let's solve some problems. Very simple problem to begin with on empirical probability. Most of the problems you will see here, I got these from the NCERT textbook. In a particular section of class 9, 40 students were asked about the months of their birth and the following graph was prepared for the data so obtained. Interestingly, here the data is given in a graph. And what did we note here? So each month, January through December, and the number of students who were born in that month. Okay. If you pick a student randomly from this class, what is the probability that he or she was born in the month of September? All right. So this is an empirical probability problem because the data is given. And interestingly, the data is given in a graph here, not in simple numbers, but it doesn't matter. It's actually simple for us. All right. So what is the total number of the probability? The probability of a student randomly picked from this class is born in the month of September. So I'm not going to write all of this down, but let's simply write as P equal to, first thing to notice, we are picking a student from this class randomly. So what are the possible total number of outcomes? Now we know this already from here. You can also add up all these numbers if you like, one by one from January to December, but that's not needed. It's already written here. So we have 40 total number of students. The question here is, what is the probability that he or she was born in the month of September? So let's see here, September month, and this is the particular bar representing September month, and I think it's this line up 3. Okay, so we have 3 students born in the month of September. Okay, the probability there is 3 over 40. Okay, can't simplify this any further. Simple. Let's look at one more problem. The record of a weather station shows that out of the past 250 consecutive days, its weather forecasts were correct 150 times. Oh, sorry, 175 times. What is the probability that on a given day it was correct? Oh, this is quite simple. So this is first problem. Okay, maybe I'll write here itself even though I have space at the bottom. So for this, what is the total number of observations? Total number of days? 250 days. What is the probability that a given day, a particular given day, the weather forecast was correct? Let's see. So the weather forecasts were correct on 175 times out of the 250. So our favorable outcomes for this event is 175. So 175 over 250. This is the probability that a given day the forecast was correct. So you can work on simplifying it. In the interest of time, I will not further simplify. You can simplify this problem. Similarly, what is the probability that it was not correct on a given day? Well, not correct. So of the total number of days, 175 days the forecast was correct. So from 250, the remaining 75 days the forecast was not correct. I'm going to just in case you're trying to understand what I'm doing here. From the 250 days, 175 days, the forecast was correct. And the remaining 75 days, forecast was not correct. So what is the probability that it was not correct on a given day? Probability of not correct is 75 over 250. This is a simple problem. Let's look at one more problem here. Oh, this looks a bit very heavy. All right, what is this example here? An insurance company selected 2000 drivers at random without any preference of one driver over another. Basically, that is saying it's random. In a particular city to find a relationship between the age and accidents. The data obtained are given in the following table. So what do we have in the table? Age of the drivers in years, 18 to 29, 30 to 50, above 50. And for each age, accidents in 1 year. So how many of the drivers have 0 accidents, 1 accident, 2 accidents, 3 accidents, more than 3 accidents. This is all put down in a table format. This is a lot of data. Find the probabilities of the following events for a driver chosen at random from the city. Right. So the driver is being 18 to 29 years of age and having exactly 3 accidents in 1 year. So 18 to 29 of age and 3 accidents. Exactly 3 accidents. Exactly 3 accidents. So that is this particular number here. Okay, so we understood here. Let's see. So the probability here is out of the total of 2000 drivers, 61 drivers, 61 drivers are between 18 to 29 of age and having exactly 3 accidents. So 61 over 2000. It's not as complex as it looks. All right, let's look at the next problem. Being 30 to 50 of age and having 1 or more accidents in a year, 1 or more. So being 30 to 50 years, 30 to 50. So here 1 or more accidents. So 1, 2, 3 and above 3. So all these 4 fit our favorable outcome criteria. So let's do that math here. I'm going to do a little slow because my pen is not helping here. 125, 60, 22, 18. So what's the sum here? So 10, 15, 3 plus 6, 9, 10, 12, and here 2, 225. All right, so the numerator is 225 and the denominator remains 2225 over 2000. That covers this problem. Having no accidents in 1 year, having no accidents. Notice here that they didn't mention anything about years of age. So it doesn't matter whether it's 18 to 29, 30 to 50 or above 50. But what matters is that the driver has no accidents, no accidents. So 0 accidents. This is the column we are interested in, 0 accidents. So how many here? We don't need to write this down separately somewhere else. Let's do this calculation. 5, 10, and sounds like 13. 1, 3. Oops. What's happening here? Did I get this right? 5, 4 plus 6 is 10, and 5 plus 5 plus 3, 1, 3, 0, 5, 1305. So having no accidents, which is 0 accidents, is 1305 over 2000. So in examinations, please do not forget to simplify these fractions always. Okay. Yeah, this looked like a big data filled with entire page, but actually reasonably simple problems. I hope you got this. So on this particular slide, I'm displaying a small quiz that you can solve yourself. So my request to you is, again, pause the video, solve these problems on your own, and come back to cross-check. This quiz is supposed to cover both theoretical probability and empirical probability. And I don't know if you remember this, but this first problem we have already covered when we were covering theoretical probability. So I'm going to skip this. You can go back to the previous quiz and check your answers there. But we look at the second problem here. What does this problem say? Class of 100 students attended an examination and secured marks as follows. All right, this is a table with marks. So 20 or less, 11 students, 21 to 40, 19 students, 41 to 60, 17 students, 61 to 80, 32 students, more than 80, 21 students. What is the probability of a student scoring more than 40 marks? Students scoring more than 40 marks. Let's see here, more than 40. So 41 to 60 or 61 to 80 or above 80. So these are three categories. Okay. In this, the students have actually scored more than 40 marks. And let's add these up. 17, plus 32 plus 21. That sounds like plus 2 plus 2, 70. Okay, all right. There are a total of 70 students who scored more than 40 marks. So what is the probability of a student scoring more than 40 marks is, what is the total number of students here? 100. Of that, 70 students scored more than 40. This one I'll simplify. 7 over 10. Easy. Alright, I hope you also got this answer right. Okay, let's now quickly revise what we have learned. So this is coming towards the too close to the end of this entire tutorial. So what did we learn? We learned about theoretical probability. Theoretical probability is about mathematically what is possible, calculating probability without any data, mathematically what is possible from a given situation. So the formula here is theoretical probability equal to number of favorable outcomes over total number of outcomes. And I've shown this in visually that typically in the tests and examinations, you will get problems of a coin or a die or multiple coins, multiple dice, or playing cards, or we didn't cover this, but sometimes you'll also get problems related to a bag. For example, in this, someone can say there is a bag with 1, 2, 3, 4, 5, 6, 6 red color marbles and 4 green color marbles. If I randomly pick one marble out of this bag, what is the probability that that marble is green color? So that would be 4 over 10, right? These kind of problems are possible with a bag of marbles or bag of anything, right? That's also possible. And other problems you will hear is something with numbers or letters, anything like that. For example, with numbers, they can say, I have cards numbered 1 to 10. If I pick one card out of it, what is the probability of that being an even number? Something like that can be given. So all of these are theoretical probability. And remember, the questions are typically in one of these 5 type of questions, and some other possibilities also. Okay, so that's about theoretical probability. What did we learn about the probability number scale and the terms related to that number line, right? So on when an event has zero probability of happening, that is called impossible event. When an event is certain going to happen, it's called a certain event. Certain event has probability of 1 or 100%. An impossible event has probability of 0 or 0%. And the equal chance events have probability of 1 by 2 or 50%, like tossing a coin. Okay, that's about probability scale or the probability number line. Then we jumped into empirical probability. Empirical probability is when we have data. And I've shown here that data can be given just as numbers as this example, or in a table. We have solved some problems using table also. Data can be given in a table, frequency distribution table or any other kind of table. Or data can also be given in some sort of chart. Okay. So data in examination can be given in multiple different ways. Okay. So empirical probability is about taking such data and being able to calculate the empirical probability. And the formula for this is number of trials in which the event E has happened, because we are calculating the probability of E. Number of trials in which event E has happened over total number of trials. That is the empirical probability formula. And I want to quickly refresh your memory that we've discussed these 4 terms related to empirical probability: an experiment, a trial, an outcome, and an event. Event is what we usually calculate probability for. So I hope this revision helped. I just want to tell you that probability in mathematics, at least in this particular tutorial, it might have sounded very simple because it's basic tutorial for grade 9. But probability, there is a lot more to study. And the empirical probability is very closely tied to statistics. You may have noticed that in statistics also they give a lot of tables, graphs, and we calculate mean, median, mode, and multiple other things. And in empirical probability, we end up calculating probability of events, very closely tied to statistics. But probability is used quite a bit in multiple fields, weather forecasting, insurance, and other financial things, stock market, sports, games. If you ever seen casino or playing cards or slot machines or multiple other games, and machine learning and artificial intelligence is very much an evolving field where a lot of prediction of things happens, and there also probability is used. So probability is a very important mathematical concept. So I hope you are quite excited to learn this today. I hope this tutorial was helpful to you. Thank you for watching. All the very best.